Every trolleybus operator knows that one of the key elements of the infrastructures are the trolleybus switches. Some of these switches are in intensive use. They are operated almost 150 or 200 times every day. After intensive usage, these switches could become unreliable, which could cause derailments of the current collectors or operational disturbance, even sometimes accidents. These switches don't become unusable, but also we didn't want to keep them in operation and also didn't want to throw them out. But there is a place where a lower safety level doesn't cause that much of operational problems, and this is the trolleybus depot. Instead of throwing these switches out, after dismantling from the network, we brought them back to the depot. There regular maintenance was done on them, and also some maintenance which caused the lengthening of the life cycle of these switches. And after that, we reinstalled them in the depot. Thus, within this CE4CE project, we could remove the old switches in the network, but reuse them in the depot. And we could even remove the even older, very outdated switches. And this could be a pilot for a future similar actions, which could replace all the outdated switches in the depot.
We are in Maribor, a city that has been strongly advancing the electrification of public transport in recent years. By 2030, the goal is to reach 50% electrified bus fleet. This transition brings two key challenges: increasing demand for electricity and pressure on grid infrastructure, and the second challenge, the growing need to manage batteries once they are no longer suitable for vehicle use. The Maribor pilot addresses these challenges through the reuse of batteries in a stationary energy storage system, supporting the grid during bus charging.
The pilot addresses the lines where energy demand is already high, as is the case of a fully electrified line here at Spenjača. Here buses are charged with opportunity charging, where typically charging power is minimum 150 kilowatts. This leads to short but high power peaks. The main role of the storage system is to smooth these peaks and reduce the required grid connection capacity. In the pilot, the system demonstrates a reduction of peak load by approximately 25 kilowatts. A key aspect in the system configuration, which allows parallel charging of both the battery storage and electric buses using energy from the grid and the storage system. The storage system is based on second life NMC battery models with a total capacity of 140 kilowatt hours. Ensuring safe and reliable operation is critical, as these batteries are classified as hazardous goods. Tests showed the importance of fire-resistant housing, cooling and advanced monitoring and safety systems. In addition, photovoltaic panels are integrated to demonstrate renewable energy use. Both batteries and solar panels are connected to an 80 kilowatt hybrid inverter, enabling operation from multiple energy sources. Scenario analysis showed that under moderate operating conditions, batteries can remain effective as stationary storage for a long time. With larger capacity, the system could also support off-peak energy use and increase energy self-efficiency.
The pilot confirms that battery energy storage can be a viable solution to growing energy demand in electrified public transport. Beyond technical feasibility, economic viability is essential. The cost-benefit analysis shows that the most effective systems are those combined with the renewable energy sources. The CE4CE project enabled us to demonstrate the circularity concept in practice. However, further development is needed to scale such solutions into fully operational and commercially viable systems.
In the city of Bergamo, the ATB Group manages through its subsidiary TEB the T1 tramway, a 12.4-kilometer high-capacity light rail line that represents a fundamental backbone of sustainable public transport for commuters and for local and regional mobility. The traditional maintenance approach for this type of infrastructure is often largely reactive. Extending the service life of the infrastructure and vehicles is essential to control cost, reduce waste and ensure reliable service for passengers. To address this, ATB and TEB worked with the Crook Railway Innovations to test a sensor-based monitoring and simulation solution. First, we equipped a standard tram operating in daily service with advanced sensors, cameras, and onboard computers. These tools continuously monitor the interaction between the pantograph, the overhead contact line, and the vehicle itself. Second, the collected data is analyzed using digital tools and AI to detect early signs of wear or anomalies. This allows maintenance teams to intervene only when and where needed. ATB aims to scale this approach to more vehicles and lines, strengthening sustainable mobility in Bergamo and beyond. This pilot shows that even small, well-targeted innovations can make public transport more resilient, efficient, and circular.
We are here in Leipzig, where our public transport network depends on reliable track and overhead line infrastructure. Like many transport operators, we are facing aging infrastructure, limited resources and growing demands. Today, inspections are often manual, subjective and sometimes only detect damage when it's already become critical. This leads to unplanned maintenance, disruptions and higher costs. We needed a smarter way to detect problems earlier and make maintenance more predictable. In the CE4CE pilot, we equipped several trams with a modular set of certified sensors. These include vibration sensors, cameras for overhead line monitoring, laser scanners for wire geometry and interfaces to vehicle data. Instead of high precision measurements at single points, our approach collects large amounts of operational data. By analyzing patterns such as shocks, uneven ride behavior or pantograph interactions, we can automatically identify typical fault signatures. Together with our partners CE4CE, Krug, CeMIT and Panto Health, we develop data platforms that visualize anomalies, trends and long-term changes. First results already show broken rails, poor track conditions and shocks at overhead line section insulators, confirmed by visual inspections and used to refine our models. These give us objective, continuous information that supports early detection and better maintenance planning. The pilot is still ongoing, but the direction is clear. We are moving toward data-driven decision-making, better documentation and fewer unplanned interventions. Our next steps include refining the predictive models, integrating dashboards into our daily operations and preparing the system for wider rollout to more vehicles and lines. CE4CE helps us shape a future where maintenance becomes proactive, efficient and more sustainable.
In Gdynia, within the CE4CE project, public transport operator PKE Gdynia explore how circular economy principles can support more sustainable bus operation. Our pilot focus on using digital tools to better understand and improve energy and resource efficiency in public transport system. Public transport operation face increasing pressure to reduce energy consumption, extend and lifetime of vehicle and infrastructure, and lower environmental impacts. To address this, the Gdynia pilot is developing a digital twin combined with an energy flow in simulation tools. The digital model allows us to simulate how energy is consumed across the entire bus system, from vehicle operation and supporting infrastructure. The Gdynia pilot demonstrates how digital simulation can become a practical foundation for circular economy strategies in public transport. By combining local operator knowledge with research and innovation, we aim to create tools and methods that can be scaled to other cities across Central Europe.
In Gdynia, Poland, University of Gdańsk and PKA were working together on a pilot of PKA Digital Twin to optimize the energy flows for Western Corridor in Gdynia, Poland. Altogether, we developed the dataset for the digital twin and also worked on optimizing the energy flows in different scenarios in order to make the best decisions in investment process and procurement process for PKA Gdynia and to provide some solutions for other public transport operators, not only in Poland but in the whole Europe and Central Europe region. This digital model allows us to simulate how energy is consumed across the entire bus system, from vehicle operations to supporting infrastructure. It helps us understand where the highest energy demand occurs and how different operational decisions, such as route planning, charging strategies, or vehicle usage, influence overall efficiency. By using this approach, we can identify opportunities to reduce energy demand, improve resource use, and support longer life cycles for vehicles and infrastructure.
This is the Tatra tram, which is running in the city for 30 years. Unfortunately, the factory support stopped, and we cannot buy any new main parts for the vehicle door systems, like the vehicle door controller unit. If the vehicle door controller unit broke down and we cannot repair anymore, we have to replace it, because without this the whole tram will be out of service. Based on the original documentation of the vehicle door controller, we redesigned the full controller unit, and after all we tested and manufactured it with modern parts and elements. We are very close to get the final certification from the authority to use these units in the trams, in the vehicle and in the city. And after that we will get a stable partner here. In the next years or decades, he can produce more spare parts for the system, and any other company in the similar situation could use the know-how of this project.